Alrighty, so in this video we're going to talk about vertical asymptotes. What makes a vertical asymptote? And we're going to talk about rational functions, start talking about rational functions in general, and we're going to graph some of those and see what's going on. So remember, in the last videos we saw that as x is getting closer and closer to 0 from the right side, as it's getting closer, f of x, the function, was getting closer and closer to infinity. Oh my goodness, that's just awful. F of x was getting closer to infinity. So as x is approaching 0 from the positive side of the graph, from the right side of the graph, y of x, or f of x, I'm sorry, the y value is going to approach infinity. This means that we have a vertical asymptote at x equals 0. Because if we're looking at our graph, so when we're looking at our graph, as my x function went like this, remember with the graph, we were close, and then it hit the 0.11, and it started going up like this. That means f of x is a vertical asymptote. I'm sorry, not f of x. X equals 0. My x-axis is a vertical asymptote. We're going to get close to that line, and we're never going to cross it. Now it said, hey, let's talk about it when we have our negative x values. Well, if we make up a chart real quick, let's approach 0 from the left hand. So I'm going to put 0 way over here. Again, 0 is going to be undefined. Well, let's come up with some really large negative, as x is approaching negative infinity. Again, we're going to have negative 1 over 100,000. But let's get down closer to what's happening here. Let's jump ahead a little bit, shall we? Let's do negative 1/10. Oh, that's going to be negative 10. So when we're really close to the x-axis, we're going to be negative 10 on the in the y direction. What if we're getting closer and closer to 0? What if we do negative 100th? That's going to be negative 100 in a y direction. Negative 1,000th. That's going to be negative 1,000 in a y direction. And what you see going on is, again, boom, we're going to get very close to the x-axis, but we're never, ever, ever, ever going to touch it. Because x equals 0 is a vertical asymptote. I'm getting very close to this vertical line, but I'm not touching it. The x-axis, y equals 0, is my horizontal asymptote. I'm going to get very close and not touch that one either. That's what asymptotes are. So in general, for any rational function, any function that's a fraction, if f of x approaches infinity as x approaches some value, in this case that was 0, then that line, x of a, is a vertical asymptote. What we're saying is my vertical asymptote doesn't have to be at 0. It can be at x equals 1, x equals 2, x equals 3. It can be at any point, any vertical point along that line. All right, we're saying that what just happened? Oh, just wanted to make sure I'm okay here. Let me see. Sorry about that. Little technical difficulties on my end. What I'm saying with either asymptote is this: in both of these graphs, if we can move, my graphs can all move like this, and this will no longer be x equals 0. This is going to be x equals a. Alrighty, so my vertical asymptote and my horizontal asymptote can both move. So let's consider our rational functions more broadly. Of course, we're going to have p of x and q of x. A rational function is a fraction. So we know the bottom can't be 0. So in all of these, f of x is 1 over x. This is a rational function, but remember, x cannot equal 0. For f of x equals x plus 1 over 2x squared plus 5x minus 3, this is a rational function. And we know 2x squared plus 5x minus 3 cannot equal 0. And for our last one, x squared plus 8x plus 16, again, cannot equal 0. Denominators of fractions can never equal 0. When it does, we are going to have a discontinuous graph. We're going to have a discontinuity of some kind. So as q, remember, any values of x such that q of x, the denominator, this q of x is my denominator, they're going to be excluded from the domain. Any value of x that I can plug in that will make the bottom 0 cannot work. They are not part of my domain. So when we look at if those values exist, we're going to have a discontinuous graph. That's going to be where we have a break in it. When we looked at these graphs, the graphs we just made, they're discontinuous because we've got these curves, and it's not one continuous graph. We can graph it like this, and then I have to pick up my pencil and come over here to continue graphing. Remember, that's what we said our definition of discontinuous was. So let's take a look at some of these reciprocal functions. So the reciprocal function f of x equals 1 over x is going to pair every real number with its reciprocal. So the reciprocal of negative 2, if we're making our graph for this, the reciprocal of negative 2 is going to be negative 1/2. The reciprocal of negative 1 is negative 1. The reciprocal of negative 1/2 is negative 2. The reciprocal of 0, pay attention, tricked you, it's undefined. Our denominator cannot be 0. The reciprocal of 1/2 is 2, 1, and 1/2. So remember, well, I've got the undefined. When I plug in a 0, the function itself ceases to exist. So if we sketch this a little bit, let's go out negative 2, negative 1/2. That's about right there. Negative 1, negative 1. Negative 1/2, negative 2. This, remember, y equals 0, the x-axis, is my horizontal asymptote. Oh, I just totally missed all those points. That's pretty horrible. Let's get rid of that. Just missed all of my points. So, you know what, let's try again. And then, of course, we're going to get closer and closer to y equals 0, the x-axis, but we're never going to cross it. We are also going to get closer and closer and closer to the y-axis, x equals 0, and never cross it. Then we're going to pick up our pencil, and we're going to come to the other side. 1/2, 2, 1, 1, 2, 1/2. And this graph, we're going to start up here. It's going to be very close to the y-axis, x equals 0. It's going to turn. We're decreasing continuously. We're getting closer and closer to the x-axis, but never touching it because those are my asymptotes. So the domain, what are the x values that I can plug into this function that will generate real y values? Well, the domain, we can start plugging in values way over here at negative infinity. I'm using a parentheses because we can't actually touch negative infinity. We can keep plugging in x values all the way up until I get to 0. But I can't plug in 0. So this is saying from the left, plug in values until you get close to 0, but don't touch 0. And then we're going to make a union because we're discontinuous. Then on the other side, we start at 0, but don't touch that 0, and keep going to the right for infinity. We can also write it as set notation, where we're going to say this is the domain is all values of x where x does not equal 0. That's another way of expressing our domain. I like this first one better because every time you get a union like this, it shows where our discontinuity is. And then the range, what are the y values that we get back out starting small to big? Well, again, we can get out incredibly negative y values, and those y values are going to get larger and larger and larger and larger and larger until we get to the x-axis where we cease to exist. So we're going to say start at negative infinity, don't touch negative infinity, end at 0, don't touch 0, hop over 0, and keep going up to infinity. And in set notation, it's going to be the value of y's, where again, y does not equal 0. So if we analyze this graph, here's a better picture of it, one I actually took from Desmos. This function decreases on our open intervals. So where is the graph going down? Well, as we read it left to right, how we read our graphs, you can see the value is always decreasing. From negative infinity to 0, the graph is decreasing. Well, as we're reading left to right, remember we're reading left to right, so then we hop over 0, and that shoots us way up here to infinity. The graph is still decreasing. Even when it turns that little corner, it's always decreasing. Where are we discontinuous at? We are discontinuous at our vertical asymptote. We are discontinuous when x equals 0. Our y-axis, x equals 0, here's our y-axis, this is where it gets a little tricky sometimes, is our vertical asymptote. It is a line I will approach but not touch. And the x-axis, or y equals 0, is my horizontal asymptote. It is an odd function. This function here is an odd function because it is symmetrical. It has this symmetry right about that point there. It has symmetry about the origin. Boom. So when we get back, in the next video, not when we get back, but in the next video, I'm going to show you how to do some shifting with a graph. So if you have any questions over anything I talked about in this graph, remember, jot it down. Please let me know when we see each other. Don't let your questions go unanswered.